There we go. All right, so all of the design documents, that's your final draft. The one that you will turn in next week is the one that will actually count towards your grade. So make sure that you're picking yours up today and looking at the feedback that we've given you so that you can incorporate that into your final draft. Many people chose not to take advantage of these 5 or 6 draft opportunities that we gave. So good luck to you with trying it just with one shot. Make sure that you are looking at the examples. Make sure that you're not plagiarizing the examples. That will result in an immediate 0. Make sure that you are looking at the professional examples. Make sure that you're looking at the rubric if you've not seen a draft copy yet. So today we're going to continue with trees and tree-based data structures. We left off last time with looking at preorder traversal. And I want to go ahead and review that now. I'm just going to draw a very simple tree here, and then we'll go ahead and do another preorder traversal on it. So A, let's say that it has 2 children, a left child and a right child, B, C. Let's say that this has a left child, D, but no right child. Say that this one has both of them, E and F. And then we'll say that E has another right child, but that's the extent of our binary tree here. So again, remember a preorder traversal is going to go in a root, then the left subtree inductively, and then the right subtree, right? So we always start at the root of the tree itself, right? And we've got A here. So we enumerate that because we enumerate the root, then we go to the left, then we go to the right. So I'm going to go ahead and enumerate A, right? And then we go to the left subtree, right? At this point, if you cut this off from everything else, you've got B and D, and so B is now your new root of this subtree. So you go, again, root, left, right. So B, and then you go down to the left subtree, which is D, right? And then there is no left child, there is no right child, so you're done with this. You recurse back up if you're looking at the recursive version of this, and then you go to the right subtree, but there is no right subtree, so you end up doing nothing. At this point, you're done with A and its left subtree, right? This is the left subtree of A. And then now you go over to the right subtree, right? Just this tree right here. Again, you go in order. Preorder traversal is root, left, and then right. So root is going to be C. And then you go left, and you see that there's E, no left subtree, and then you go right. So it's going to be E and G. Then you're done with C's left subtree. So you come back up. You've already enumerated C, and so now you go to F, right? So if you want to look at this from the perspective of each one of these things, A is going to do the left subtree and then the right subtree. And then if you want to look at a subtree from the perspective of a subtree, right, we're looking at C and its left subtree and then its right subtree, right? And that is preorder traversal, right? Now I want to rewrite the pseudocode that we did last time. I'll come back to this maybe. Let's go ahead and write not the recursive version of it, but instead let's go ahead and write the stack-based version of it. So preorder traversal. I'm at an angle today, so please let me know if it's off of the. Let me go ahead and move this so I can actually see it. All right, preorder traversal. And we're given a tree, so the input is a tree. I'll just call it T. And we'll assume that we have access to the tree's root. Okay? Our output is going to be a preorder traversal of T. Now remember, you're creating this tree to be a data structure. A data structure is created to hold things. So ostensibly, you're storing data in this tree. You basically want to process it. What do I mean by processing? Well, what we've done so far is just simply outputting it. But your processing could be anything. If you're storing invoices in it, then you could compute the total of the invoice and then print that out. If you were storing products, you could you could compute the new price of a product or something like that. Whatever data you're storing in here, processing means different things. So I'm going to keep this general. This is, again, pseudocode. And by process, I'm just going to write process the node or process the data in the node. Okay? Now, remember that we're going to do a stack-based tree traversal here. Right? So what I'm going to do is I'm going to start with an empty stack. Right? So S is going to be my empty stack. Now, to get things started, we need to start at the root, right? So I'm going to push t's root, and I'll just use the dot operator here. I'll steal that from C and C-based languages. The indirect component selection operator, the direct component selection operator is what it's called in C. I don't know what other people call it. It's the dot operator, right? You push t's root onto S, right? And that sets me up. Right? Remember that if I was doing it on this tree, I would need to start at A, so I'm going to create a stack, and I'm immediately going to push A. Then I'm going to pop it off. Remember, there are 3 steps that we looked at last time. I'm going to pop off whatever on the top of the stack, process it, because that's the root, and then I need to make sure that I don't forget that I need to take care of the right subtree. So I'm going to push the right child, then I'll push the left child in that order. Remember, I screwed that up. But not because I didn't remember it, but because I screwed up my left and right. We're going to push the right so that it looks like, once this is popped out, C and then B. So that on the next iteration, what do you have at the top of the stack? You have the left subtree. You go down and you complete the left subtree, filling up this stack, popping things off of it until you get back down to C here. You didn't lose it, right? That was your breadcrumb to remind you that you still need to take care of A's right subtree. Right? So I'm going to go into a while loop. While S is not empty, I'm going to go ahead and pop whatever's on the top of S. S dot pop, say. Right? Whatever that is, I'm just going to call that X. I will process X, right? And then move on. Now I need to push the right child and then the left child in that order. So push X's dot right child, and then push X's left child. And again, this is pseudocode, so I'm skipping a few lines here. In particular, it would be helpful to say, well, if there is no right child, then don't bother, right? So if the right child exists implicitly here, then push it. If the left child exists, then push it, right? Onto S. Onto S. And that's it, right? Extremely simple. In fact, we're going to come back to this. I'm going to leave it up here because I'm going to show you some other traversal algorithms before we. And I want to draw a callback to one of the themes of this course. But basically, what are you doing here? You're putting stuff in, or you're putting stuff in to a data structure. You're taking stuff out. Putting stuff in, taking stuff out. Right? It's the real power here is your data structure itself. Smart data structures and dumb code are a lot better than the other way around. This is dumb code. While I still have something in my data structure, put something in, take something out. Put something in, take something out. Right? And so this is extremely simple. Simple code, dumb code, but a smart data structure that guarantees you LIFO ordering, which gets you this kind of structural behavior when you perform it on a binary search tree. Or a binary tree, excuse me. We haven't gotten to binary search trees yet. But before we go on and look at some other options and different options here, I want to go ahead and analyze this. Right? I won't go through our usual 5-step process here. Instead, I'm just going to make a few observations. For each node is processed how many times? Do you ever process a node twice? No, once. For each node, how many times did you end up putting it in a stack? Each node is pushed. How many times? Once. And if it's only ever pushed once and you continue until it's empty, then it's only ever popped once. Popped once. Right? So how many nodes do you have? The number of nodes in a binary tree, maybe this was implicit last time, but I'll be explicit about that now, is in general n. We use the variable n to denote the size of input. Well, that's the size of your tree, right? And we already observed that if you have n vertices, n nodes in a tree, how many edges do you have in a tree? N minus 1. So there's a direct correlation there. They're both order n. And so if each node is processed once, pushed once, popped once, it doesn't matter what you look at as your elementary operation. This one is probably the most appropriate, right? Because pushing, popping, that's necessary for the control structure of your algorithm. That's quite efficient if you use a linked list. Each one of these things is an order 1 operation. This one is probably the most expensive and the equally common one among all 3 of these. So you would say that this algorithm is order n. Right? Now remember that our motivation for this was to eventually get a data structure where all of the operations are proportional to the depth, order log n. Now this is not one of those operations. This is something different. It's not inserting stuff, it's not deleting stuff, it's not retrieving stuff. In a way it's retrieving stuff, but you already resigned yourself to the fact that I'm going to process every single node. Well, you can't do better than that. If you want to process n things, you got to do n things, right? You've got to do n process operations. So this is definitely order n, okay? That's as good as it gets as far as if you've resigned yourself to having to do something with every single node, okay? It's kind of like linear search too. Your processing could be that you're searching for a particular node with a particular key value. And if you have no other structure other than just a binary tree, well, you have to look at everything, right, potentially. Maybe you find it at the last one that you looked for, okay? All right. I really like this tree, so let's go ahead and do some other operations on it, okay? There's not just preorder, right? There's also in-order traversal, and what's the opposite of pre? Post. Postorder traversal. All right? So those are it's very slightly different. With a preorder traversal, you go with the root, then you go to the left, then you go to the right. With an in-order traversal, the only difference is where you do the root. So you do the left subtree first, then you do the root, and then you do the right subtree. Right? And with a postorder traversal, note here that we're just moving the root over. You do root left root right, or what's the last one? You would do the left subtree, then the right subtree, then you would do the root. Now, combinatorics, you've got 3 different elements here, root left right. So how many permutations are there? 3 factorial. So that's 6 orderings, right? I only have 3 here. The 3 other orderings are where you go, instead of going left right, you go right left. So you could go root right left. You could go right root left, right left root, right? You could do all 6 if you really want to, but we really don't pay attention to that because, again, these data structures are holding things. We like to think of it left to right, top to bottom. You could go from the right to the left, but guess what I could do? I could take your tree and then just rotate it around. And guess what happened to your going right now? Now you're going left instead. So it's just all a matter of perspective. And there's no point in looking at things that go right down the right subtree first versus the left subtree unless all it is preorder traversal on a reversed tree, right? Treating left children as right children and vice versa. That's why we don't have those 3 other traversal strategies. So let me go ahead and go through this tree again, but in an in-order traversal, right? So ignore this. We'll ignore this here. So I'm going to the left subtree first. I always start at the root, but I don't immediately process it. I don't immediately output it because I'm going to do the left subtree, and then when I'm done with the left subtree, I come back up and do the root. Right? So I will go down to the left subtree here. This is now my new subtree. I've got B and D. So what do I enumerate next? Do I do B immediately? Nope, because I need to go left before I do the root. So I'll go left. Now I've got a single root node, or I've got a single node here in D. Right? There is no left child, otherwise I would have gone to it first. Right? So you can already see that an in-order traversal traverses all the way down to the left before it does anything. Right? So I do the left, then I do the root. So the first thing in this order, in the in-order traversal that I do is D. Then I do its right subtree, but there is no right subtree. Come back up. I've already done the left subtree. Now I need to do the root, and then the right subtree. So the root here is going to be B, and then there is no right subtree, so there's nothing to do there. Come back up. Now I've enumerated the entire left subtree of A. Right? This is the left subtree of A. Now I go ahead and enumerate A. Because I did the entire left subtree, now you do the root. Now you need to go down and do the right subtree. So there's my new tree. What do I do next? I don't do C, do I? Right? Because that's the new root. I do that after I do C's left subtree over here. So the first, I go down to the left subtree. Right? Now what do I do? I go to the left subtree, but I see that it's not there. Right? So I don't end up doing anything with it. And so I enumerate E. Right? Then I do E's right subtree, which is G. Right? Actually, when I go down to G, I do the left subtree, then I have the right subtree, but there's nothing there. And so now I come back all the way up to C. Right? I do C, and then I do its right subtree, which is just F. Right? So this now is, with respect to A, that's A's right subtree. If you want to look at the subtree E, this is its left, and this is its right. Right? So it's completely different. Here. It's completely different ordering than what we had with a preorder traversal. And that's okay. Each one of these things has its own applications that we'll talk about later. Okay? What about a postorder traversal? Right? We do the left, then the right, then the root. So predict immediately, what is the very last thing that I'm going to write down? A. Right? What's the very first thing that I'm going to write down? I go all the way to the left until it has nothing left. So it's going to be very similar to an in-order traversal. Right, I start here. I don't do A. I do its left subtree first. I don't do B. I do its left subtree first. I don't do D. I do its left subtree, but it's empty. Then I still don't do D. I do its right subtree, which is also empty. So I end up doing D first, similar to this, but dissimilar from preorder traversal. Or was it? I forget. Nope, yeah, well, obviously it's A up here. All right, so I come back up here. I don't do B immediately. I look and see, oh, right subtree, it's empty. If there was something there, I would have done that next. And then I do B. Now I come up here. I've done A's left subtree over here. Do I now do A? That would be in-order traversal. I need to do the right subtree before I do A. So I'm going to go ahead and come over here to the right subtree. What do I do next? I need to do C's left subtree. I have E. I need to do E's left subtree, which is empty, nothing. Come back up here. I need to do E's right subtree, which is G. And then I do E. Right? Then I come back up here. I'm still not done. So with this subtree here, I need to do the right subtree first, which is F. And then I can do the root node of this, so C. And then I'll have A right here, right, at the end, as you predicted. Okay? So again, from the perspective of A here, where is its left subtree? It was C, E, F, G, right? So here's its, this is its right subtree, and here's its left subtree from A's perspective. From C's perspective, and I'm only going one level down here, from C's perspective, its right subtree was right here. This is the right. And then this was the left right here, these two nodes together. Right? So it's not exactly a mirror image, is it? Let's go over here. Well, maybe, I don't know. In some instances, you could get a mirror image, particularly if it's a full tree, but I don't think that we'll get it here. If I just go in reverse here, I see it's not just reversed. So it's not simply a matter of taking a preorder traversal, flipping it around, and then getting a postorder traversal, right? This thing is not this thing backwards. It's telling you the structure of the tree, okay? Okay, so that's in order, postorder, preorder. Let's look at an in-order traversal here, and hopefully you remember the recursive version of the preorder traversal. If not, we can do it really quick over here. Recursive preorder. I'll put even more terse pseudocode here. What are we going to do? Well, our input is a node, u. And so what we're going to do is we're going to immediately process it. Process u. And then we're going to recurse. We're going to recurse first on its left subtree, and then it's on its right subtree. So we'll go ahead and call preorder on u's left child. And then we'll go ahead and call preorder on u's right child. All right? This is what we covered last time. I wanted to remind you of this because what would an in-order traversal look like recursively? So recursive in order. What's the first thing we do now? Over here, the first thing we did was process the root. But remember, an in-order traversal, you go down to the left subtree first. So it would be in order of u's left child. Then what's the next thing we do after we're done with the left subtree? We process the root, process u, and then we go down to the right subtree in order of u's right child. Remarkably similar, right? What's the difference here? Well, other than the name, where we're processing u. I process it first, or I process it in between. What do you think postorder looks like? Postorder of u's left child. Then you do the right, postorder of u's right child. And then what do? You process u at the end. Right? So all it is two recursive calls, and the only difference between each one of these three is where you process u. You do it before the two recursive calls, in between the two recursive calls, or after the two recursive calls. But otherwise, the recursive calls, other than the name, is exactly the same. Right? All of them are going to be order n. You're not doing extraneous work like you do with recursion, where you do the Fibonacci sequence recursively or something like that. Right? So this is as close as I will ever get to advocating for recursion. Right? Because, yeah, that's pretty simple. It doesn't get any simpler than that. Right? And you don't have all the negative byproducts of using recursion while you are still abusing the stack a little bit. And so if you do have a very, very large tree with a very, very large depth, then you're going to have a very, very large stack, call stack. And if you're in an embedded system, you can't afford that. And so you could put an in-memory stack instead, like we did with this algorithm. Right? No recursion here. Instead, we're simulating the recursion using a smart data structure. Right? Let's do the same thing for in-order traversal using a stack instead. Right? But before we do that, let's think about what we need to keep track of. Here's a parent. Here's u. Say it's a left child. And then we've got a left child and a right child hanging off of u. Right? Now, an in-order traversal means that I need to go down to the left subtree and then eventually come back up here, process u, and then go back down to the right subtree. Now, we're going to be visiting, in essence, conceptually, we're going to be visiting u a few times here, right? Once when we come down from the parent, once when we come back up from the left child, and at which point we need to process this, and once when we're coming back up from the right child, which we don't care about yet, right? We would care about this in a post-order traversal because we would need to distinguish between, are we coming here for the first time, in which case we do want to enumerate it because it's a preorder traversal, or we're seeing this for the second time, in which case if it's an in-order traversal, that's when we process it, or we're seeing it for the third time, in which case that's when we process it because that's a post-order traversal. So in other words, we need to distinguish two cases. Is this the first time we see U, or the second time? Right? And then the third time, you'd need to distinguish that for post-order traversal. I'm just going to go ahead and focus on these, though. So if this is the first time that we are going to see this, then what do? If it's the first time, don't process it. Right? Instead, what are we going to do? We're going to need to remember that we need to come back here and then process it eventually. Right? So don't process it. Instead, store it. How are we going to store it? What kind of data structure? If you need to remember something, where you've been and where you're returning from, then what kind of data structure gives you that? What kind of data structure gives you breadcrumbs? A stack. Right? If it is the second time, then, in other words, we push it. Right? If this is the second time that we've seen this, then we're going to process it. And then we've popped it off the stack. That's the basic idea. We need to be able to distinguish between these two cases. Okay? So let's go ahead and start some pseudocode here. Sorry. Again, this is an in-order traversal, so it's going to be a stack-based in-order traversal. So our input is going to be the same. It's going to be a tree, T. And our output is going to be an in-order traversal. Output is an in-order traversal. We're going to have a very similar code from before, pseudocode at least, where we create an empty stack. That's where we're going to be storing our breadcrumbs. Where have we been? Where are we going to? Is this the first time that we've seen this or the second time that we've seen this? And general graph algorithms will actually use colors on vertices. This white vertex is a vertex that we've not seen before. The first time we see it, we color it gray because we've been there. The last time that you see it, you darken it out and color it black, and so you've got white, gray, and black vertices indicating what have you not seen it yet? This is the first time you've seen it. You have seen it, and then maybe this is the second time that you've seen it, or it's done. You're done processing it, and it's no longer there. The only reason that they use white, gray, and black is because color printing costs a lot. Otherwise, they would have done something green, red, and yellow or something. All right. But the color ink is very expensive. Right? We're going to initialize U here to start at the root. Right? U is basically going to be our current vertex, right? Well, like I was writing over there in when we need to distinguish between. Have we looked at? We're standing on a vertex right now. Is this the first time that we've seen it? In which case we need to store it off and remember it, or is it the second time that we've seen it? We need to process it now because it's an in-order traversal. So I'm going to go ahead and go into a while loop here, but we need two conditions to be able to continue. The first condition is still the stack. While the stack S is not empty, but you'll see immediately that it is empty. We never pushed anything to initialize. So if this was the only condition, this loop would never execute. So we need to have another condition, or U is not nil, null, phi, whatever flag variable you want here. U is not null or phi or whatever because it right now has the value of the root. So this second condition here gets us into this while loop. Now, again, we need two conditions here. We're going to be able to distinguish between these two things by looking at U and seeing, is it null, or phi in this case because of pseudocode, or is it not null? If it's null, or if it's not null, which one is first? Yeah, if U is not nil or phi or whatever, then I'll go ahead and push U onto S. In other words, this is the first time I've seen it. Here's my root. I haven't processed it yet. It's not null, therefore it's the first time I've seen it, and so I need to push it on the stack to make sure that I come back to it later. And then I need to go where? I've pushed U onto the stack. Let's look at this from this perspective. I've pushed U onto the stack. Where do I go next? I've saved it off so that I'll process it later. Where do I go next? To its left child, right? Because it's left, then the root, then the right. So I will update U to be U's left child. Right. There we go. The other case is when I'm coming back to it. Else, if U is null or nil, whatever, right? And this is not necessary here. I'm being explicit about it though. It's just an else statement. It's either equal to null or it's not equal to null. There are only two cases here. But in this case, I go ahead and pop whatever's on top of the stack, s.pop. And then now it's no longer nil, so I can actually process it. Process U. Right? And then I need to set myself up for the next iteration. Right? So where am I going to go after I've processed it? I've gone down to the left subtree. I've processed everything over here. I've popped off U. I've processed it. So where do I go next? The right subtree. And I update U to be U's right child. And that's all there is to it. Right? Again, the only difference between an in-order traversal and a pre-order traversal is the order in which you process the nodes. And with this picture, again, all you need to do to distinguish it, if it's the first time you've seen it, there's no case that you need to take care of. That's why we didn't have an if-else-if condition on the pre-order traversal. But if it's the second time that you've seen it, then you do need to distinguish between those two cases. If it's the third time that you've seen it, you need to distinguish between whether or not this is the first time, the second time, or the third time that you've seen it. So I'm not even going to write down the pseudocode for post-order traversal. It's in the book. It actually has, I say that there are three cases, but the actual implementation has two big cases and then three sub-cases in each one of those things. Right? So again, this is going to be order n. Because you're processing everything exactly once, you're pushing everything onto the stack exactly once, you're popping everything off the stack exactly once. Right? But I do want to look at a more general algorithm here, just because I think it's fun. Right? Well, actually, two more general algorithms. You actually don't need any data structures at all to do a tree walk. Right? Tree walk. Let me go ahead and copy this tree again. Where is it? Where's that tree? It was a nice tree. There we go. So A, B, down to D, and then C over here. And then we had two children, E and F. And then E had a right child. Okay? And I'll go ahead and do this with a pencil here. Basically, I'm going to walk around the building, right? So if you go out here to the front of the building and you walk around the building, all you have to do is, even a blind person can do this. All they need to do is put their right hand on the wall and just keep walking. The second that you hit a curve, what do? You put your hand around the curve and keep walking, right? Until you get back to where you were. So this is not a building, but I can still walk around it. I can walk around the perimeter of the tree. I will start at A, go down to B, right? Go over to D, and at this point, I'm basically going around the corner of the building. And so I can come back up, and now here's like an inner corner of the building. So I can go ahead and go back down, go back over, walk around that corner, and then walk around this corner right here, go back up, keep going until you've walked around the perimeter of the tree, or the perimeter of the building, and now you're back to where you were, right? It's just by putting your hand across the contour of a shape, right? And this is a tree walk. You don't need a data structure here at all. All you need to do is distinguish where you are and where you came from. So all you need is a current vertex or current node and a previous vertex. Okay? Why is this the only? You don't need a stack. A stack could hold 1,000 elements, right? That would require additional memory. If you're an embedded system, no, you can't do that. That's too much memory. So you can actually do a tree walk only using 2 variables. All you need to do is distinguish where you are and where you came from. So, for example, let me go ahead and draw. Let's focus here on B. All right. If my previous, here let's look at it more generally here. Here's a parent. Here's the current node. This is a parent, not previous. Here's the current node. Here's the left child, and here's the right child. All right. So this is my current. Current is current. If the previous is the parent, where do I go? So I've got a situation here where this is the previous and this is the current. So in other words, which direction did I come? I came that direction. Where do I need to go next? That direction. So go to the left child. All right. Now, what if the situation is different? What if the previous is actually the left child? Right? This is the previous, and I'm coming up to current. So if the previous is the left, then where do I go? In other words, I'm coming back up to the current. Where do I go next in a tree walk? I go to the right. Go to right child. And the only other case here is if this is the previous, and I'm coming back up to current, in which case I've gone down the left, I've come back up, I've gone down to the right, and I've come back up. What's the only thing left for me to do? Go back. So if it's the right, then go to parent. Right? That's a basic tree walk algorithm, and you can get all 3 enumerations just simply from 2 variables if you really wanted to. Right? Which one of these situations would correspond to a pre-order traversal? If the previous is the parent and this is the current, what should I do? If it's a pre-order traversal, I came from the parent and I'm right here right now. I process the current, right? So process if preorder. Otherwise, don't process that. Instead, go down to the left child first, do everything down there. When you come back for an in-order traversal, that's when you process the current. And process if in order. Right? Otherwise, if you're coming back up from the right, you already did the left, you already did the right, and now you come back up, and now you want to process the current, then that corresponds to a post-order traversal. Right? So I've shown you 3 ways here of doing it. You can do it with recursion and abuse the stack. You can do it using a smart data structure like a stack, and then you don't have to use recursion. Or if you are in a situation in which you can't afford any extra memory at all other than 2 different variables, you can still do it. Right? All you need to do is keep track of where you are and where you came from. And of course, when you move on, when you go to the left child or where you go to the right child or you go back to the parent, you do need to update the previous vertex and the current vertex. Right? And for the full pseudocode, it's in the book. Okay? I want to show you one more way of doing it. Right? Here's another. Here's the same tree as before. A, B, C. Left child of D, E, F, and G. Right? Now remember, I told you 150 years ago, Cayley drew his first, was the first paper to actually look at trees, drew them growing downward, and that's because he envisioned that we're holding data or we're holding values in these trees. So we want them to grow downward, unlike natural trees, because we want to read them top to bottom, left to right. So read this with me, top to bottom, left to right. What's the first thing you see? A. Go to the next level and read it left to right. What do you see now? B, C. Go to the next level. Read it left to right. D, there is nothing here. E and F. D, E, F. And then finally the last level, many of them are missing, but there is one there, G. Now, this is just, don't read into anything that this is in alphabetical order. It's only in alphabetical order because that's how I naturally drew it, right? I'd have to try really hard to draw a tree that would not end up like this, right? It's just natural to draw things top to bottom, left to right in order, right? But sometimes you might want this ordering, okay? So for example, what if I wanted to start at the root, that is A, and process it, right? But then I want to ensure that its two children are processed next. So in order, left to right, right? And not in order traversal, but in the order of I want to do the left child first, then the right child, right? So I need to process the roots left, then process the roots right. Now, I need to remember that, well, I also need to do B's children and C's children, but I want to make sure that I do B's children first and then C's children, right? So, in between here, I want to process the left and the right child. There is no right child of B, but I'm always going left, right, 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 right? In that order. What does that look like to you? Let me go ahead and connect this with a line. Let me go ahead and connect this with a line. Go ahead and connect this with a line. Over here, here's the ride. You get to ride the roller coaster now. Why? You waited, you started here, and then you waited until you finally got to the end of the line, in which case, now you can ride the roller coaster. What is this thing right here? What have I been calling it? A line. What's another name, British, for line? Queue. Right? Maybe I can get this with a queue-based data structure. Right? The idea being you start at A and you enqueue it. Then that'll be at this end of the queue. Then I take things out, and A is the next thing I process. Okay, well, I go ahead and enqueue B and then C. And then at this point, A is out of the queue. Right? Maybe I should do doing this in pencil so I don't cross them all out. Right? Then I take B out, and I do its left child and that's right child, but there is no right child. So I go ahead and put in, D next. Then I dequeue, and now I've got C. C, I do its left child and its right child, so E and F. Right? And then I do that I take care of. D is done. Then I did D, but there's no left child. There is no right child. And so what's left? D should have been over here, right? Oh no, D is it is over here. Then I enqueue E and F, and then take care of E, but enqueuing G, take care of F, and then G is done. Right? In other words, A, B, C, D, E, F, G. The same exact ordering as up here if I read it top to bottom, left to right. Right? So generalizing this here is that I need to process it. Forget about this for a moment. I need to process the root left, the roots left, and let's go ahead and generalize this so it's not just root, but instead U. Use left, use right. That's my third step here. And by process, I need to eventually process them. So I will enqueue, use left. I will enqueue, use right for later processing. Let's go ahead and write that pseudocode. This is, by the way, this is called a breadth first search of a tree. Why is it breadth first search? You start at an origin and then you work your way out, right, to nodes that are a distance 1 away. Then you do everything that's of distance 2 away. Then everything that's distance 3 away, distance 4, distance 5, distance 6. In other words, if you looked at this not as a tree-oriented tree, but instead spiraling out, you're basically looking like a search pattern. You start in the middle, and then you search a perimeter of, say, 100 feet. Then you search an outer perimeter of 200 feet, and then 300 feet, or however big you want of a search pattern you want. And that's why it's breadth first, that you're looking at closer things before you go deeper into the graph, deeper into the tree. Right? The breadth first search is going to be an input of a tree, T. Right? And our output here will be a BFS of T. Right? Now, instead of a stack, we're going to want a data structure that guarantees us this line, this first in, first out data structure. So I'll go ahead and create a queue, and I'll call it Q. Right? So this will be an empty queue. What's the first thing that I did when I did this walkthrough here? I enqueued the root. So NQ T's root into Q. Right? What do you think my stopping condition here is? Once I got rid of G, then what does this Q look like? It's empty. Right? So I will continue while there's still something in the queue to process. So while Q is not empty, then I'm going to go ahead and dequeue it, dequeue whatever's in there. Q dot dequeue. It doesn't matter if you process it right away or if you push its children. I'll go ahead and process it. Process X. Right? And then we need to make sure that we do eventually its left child and its right child in that order. So NQ X is left child into Q. NQ X is right child into Q. That's it. That's all there is to it. Now at this point, hopefully I didn't lose it. Yeah, here it is. At this point, well, first of all, what about the efficiency of this? Now we're not talking about pushing and popping. We're talking about enqueuing and dequeuing. But every node is enqueued exactly once. Every node is dequeued exactly once. Otherwise, you would never stop. And every node is processed exactly once. So this is still going to be order n. It just gives you a different way of processing the tree. Nearer things first before you move out deeper into the tree. But what I want to do is I want to bring your attention to these two things side by side. Right? I really wish pseudocode had like a diff feature, a get diff feature here, because what are the differences? Right? We'll start here. What did we initialize? A stack and a queue. Otherwise, both of them put the root into that data structure. Both of them continued until that data. Oops, sorry, this is not it. Where's my other one? That's my in-order traversal. Here's what I wanted. Here's the pre-order traversal. Sorry. There we go. Now look at them side by side. Right? So the only difference is a queue over here, a stack over here. But both of them put the root into the data structure to start with. Both of them continue while that data structure is not empty. The only difference, this is a pop and this is a dequeue. In other words, you're taking something out, taking something out. Putting something in, taking something out. Processing it, exactly the same. You go right, then left. Here you go left, then right. Right? So these are essentially the same, they're just reversed. So what's the only difference here, essentially, other than this order right here? This is put stuff in, take stuff out. Put stuff in, take stuff out. This is also put stuff in, take stuff out. Put stuff in, take stuff out. What's the key difference, though? The data structure that you're using. Right? Nearly the exact same code gives you completely different results in behavior. But they're both extremely simple. You're putting stuff, it's dumb code. You put stuff in, you take stuff out. You put stuff in, you take stuff out. The real difference here is the smart data structure. One is giving you LIFO order, another one is giving you FIFO order. Right? And it gives you completely different results, both of which have their own applications and their own uses and own advantages. Okay? So again, this goes back to one of the themes of this course. That smart, it's a quote by Eric S. Raymond, smart data structures and dumb code are a lot better than the other way around. Right? If you can do 90% of your coding by simply just taking an off-the-shelf data structure and knowing its properties, knowing that it's efficient, and knowing the behavior that it gives you, and you could just write some glue code to put some stuff in, take some stuff out, awesome, because now 90% of the work is done by the data structure itself, and you don't have to worry about it. Right? Okay. Let's see. Went there. Okay. So, with how much time do we have? Yeah, with the last 20 or so minutes of today, we looked at the trees have a lot of structure. Binary trees have more structure. I want to add yet more structure. Right? So we're going to be looking at binary search trees. Right? There's really no ordering with this tree here, right? I just went in this order because I knew my ABCs, A, B, C, and I went top to bottom, left to right. That's really not going to help if you need to search for a particular key in this tree, because if you want to search for E, well, there's a big gap here. There's more gaps over here. How do you know that it's over here and not over here somewhere? I could have permuted these and randomly written A through G, and you would not be able to tell. You'd have to process everything, do a linear search using a Treewalk or a Preorder traversal or something like that in order to find the key that you're looking for. So what binary search trees do is they add a little bit more structure. It's a binary tree where every node may have data, but also essentially they have a key. Every node has a unique key value. Now for us, the key value is simply going to be an integer. I'm going to work in positive integers. It doesn't matter. You can base your key value on your object by using, say, a hash code value, right? A hash code takes the state of an object in Java and produces an integer value that then you can use as a key, right? That's not necessarily unique. Hash code values can be the same for two different objects. Hopefully you don't have that, but it is possible to have that if you've got a small domain on your codomain on your hash function. But that's why it uses both the hash code and the equals method in Java to distinguish those two. But for us, we're going to say that everything has a unique key value. If you have a situation where you want two things in your tree with the value of 10, you can do that, but it's easier if you just distinguish them. Here's 10A and here's 10B. Well, this one comes before this one. You just need a tiebreaker somehow. Okay? We're just going to put on that everything has a unique key value. Right? For every node, all the nodes in its left subtree have a key value less than it. And for every node, all nodes in its right subtree have a key value greater than it. Right? So if you want to look at this pictorially, say that I've got a node k here with a key value of k. Everything hanging off in its left subtree here is going to be less than k, strictly less than k. Again, we're only allowing unique values here. Again, another technicality is if you don't want to allow if you want to allow duplicate values, that's fine. You just need to say that this is less than or equal to k. So you're putting everything equal to the left subtree or everything equal to the right subtree. You just have to be consistent about it. But we're not going to look at that. Instead, we're going to just not have to worry about that technicality and go with uniqueness. And everything over here is strictly greater than k. Gee, that looks familiar. Something in the middle such that everything over here is less and everything over here is greater. Let's go back to a picture that I drew before. 10, 20, 30, 40, 50, 60, and 70. What if this were an array? And you wanted to search for, say, 15. How would you go about doing this? Given that this is sorted, you would jump to the middle, right? And you'd say, I'm searching for 15. 15 is strictly less than 40, so where am I going to go? I'm going to go onto this half of the list, effectively cutting out half of the array. Now I'm going to go ahead and jump to the middle here because I have random access. This is an array now, right? I have random access. I can jump to these things. I would not be able to do this with a linked list, right? So I'm going to go ahead and jump to the middle here and say I'm still looking for 15. And so that cuts out this other half of the list, which is now a fourth of the list. And so I look over on this part of the list, and I jump to it. Of course, I can see that 15 is not there, so it ends with an unsuccessful search. Only 1, 2, 3 comparisons to realize that that doesn't exist. Whereas if you did linear search through this, you'd have to do 7 comparisons because there are 7 things, right? Take this and reimagine this now as a binary search tree. What goes at the root? 40. Everything in the left subtree is going to be less. Everything in the right subtree is going to be greater. So in the left subtree here, I will go ahead and put the middle element here, 20. Right? And then in its left subtree will be everything over here. Its right subtree will be everything over here, 10 and 30. And over here would be 60, 50 as a right child of it, and 70 as a right child of it, or left and then right, right? So I've reimagined this array, which requires that the binary search on an array requires that you have random access so that you can jump to the middle. We no longer have that restriction. The middle, it is automatically given to you by the structure of the structure of the data structure. Where's the middle, effectively? It's at the root. Right? So if you want to search for 15, what do you end up doing? You come in here, you're searching for 15. And by the way, where do you think these things get their name? Binary search trees. It's because searching can be done efficiently. You come in here, 40. Okay, well, if 15 exists, where is it going to go? Because this is where is it going to be? Because this is a binary search tree. On the left. Everything over here is greater than 40, just like everything on the right side of 40 in the array is greater than it. So I know that I just need to go down here. That's one comparison right here. Once I'm at 20, oh, well, it's less. So another comparison right here to go down here. And oh, it's greater than 10. So I go over down here and see, oh, it doesn't exist. And it's ended in a failed search. How many? So this was another comparison right here. How many comparisons did I end up having to do here? 1, 2, 3. How many comparisons did I have to do for binary search? 1, 2, 3. Right? So you have the same potential as binary search. You have the same potential as order log n. Right? Now the problem is, again, what I talked about last time, you don't necessarily have a balanced binary search tree. Characterize the depth over here. If this was 10, then 20, then 30, then ... 100. What's the depth of this tree right here? Now realize that there are 10 elements there. Careful. What's the depth? What's the depth of 10? 0. So if we start at 0, what would be the depth of 100? 9. So the depth of this tree is 9. Depth is 9. How many elements are in there? 10. So in other words, the depth is going to be order n in the worst case. What is this thing again? It's linear, yeah, definitely. What is this thing, though? It's not a tree, really. What is it? It's a linked list. Right? So in the worst case, a tree, a binary search tree, can devolve into no better than a linked list. This over here is called balanced. In other words, there's roughly half of the other elements in the left subtree. There's roughly half of the elements in the right subtree, and that's true all the way down. This one is actually perfect. This is why I chose only 7 elements, because I knew it would end up being perfect. Right? This is the ideal. This is what gets you where the depth is order log n. Over here, the depth can be up to order n. Right? This is the ideal. Unfortunately, we're not going to get there, but we will get close to it with something called a heap next week. Right? Okay. With the last few minutes here, I showed you how to search, right? That you start at the root. Let's go ahead and codify that a little bit. Searching a binary search tree. Right? We'll just sketch this as an outline, right? So one thing that you do is you start at the root. At the root. Right? Say that we're searching for k, right? Some key k. We start at the root, right? If the current node's key is equal to k, what should you do? For example, what if over here I was just searching for 40, right? You get here to the root and you immediately find it. Is there a need to go to the left subtree or the right subtree? No, you found your needle in the haystack. That's what you were looking for. So you can stop prematurely. And in this case, it only required 1. Just like in binary search, if you were searching for 40, you jump to the middle and say, oh, okay, well, right there it is. I don't need to do any more. Right? So if the current node's key is k, then stop. Then stop. Output the current node. If you're actually wanting to output the node or the data in the node or something, whatever details you want to fill in yourself. Otherwise, else, if the current node's key is less than k, then where do we want to go? Sorry, maybe it's an awkward. I put it awkwardly. The current node is less than the key. So say that I was searching for 50, right? The current node is less than 50. So where do I want to go? I need to go to the right, right? So I will traverse right to the right child. Right? In other words, another way of putting this is update the current node to the current node's right child. There's only one other case here, else if the current node key is greater than k, then where do I want to go? I want to go the left, right? So traverse left. In other words, update the current node to the left child. Right? This is my outline. Okay? What is my other stopping condition? Over here I was searching for 15, right? How did I know that I was at an end? Here's the current node, 40. Oh, it's less, so you need to go to the left. 20 is my current node. It's less, so that you need to go left. 10 is my current node, so I need to go right because I'm searching for 15. At which point I'm done because I've fallen off the end of the tree. Right? I've gone past any leaf. So what's my stopping condition? Current node, current node, current node. Current node is now null, nil, phi, whatever flag value you want to put in there. Stop. Unsuccessful search. Right? So all of this is wrapped in a while. While down here. while the current node is not nil, phi, whatever, then continue this process. Right? If, however, you break out of this while loop and now the current node is phi, then what can you say? Output unsuccessful search. We've already taken care of a successful search here. If you find something that's equal to the key, then you output it. This looks eerily familiar. What does this look like? A while loop with 3 conditions where you update to go into, you stop because you found what you're looking for, you go left, you go right. Otherwise, if you get out of the while loop, then you're done with an unsuccessful search. That looks eerily familiar. What is that? That's binary search. Binary search had a while loop. But instead of talking about nodes and keys and stuff, well, you talked about keys, but instead of talking about nodes and going left and going right, you talked about indices. You jumped to the middle, which was the current left index, the current right index, the average. Right? Add those together, divide by 2 if it's pseudocode. Right? And then you jump to the middle and you say, oh, this is equal, in which case you stop, or it's greater, in which case you go to that direction, one direction or the other. Right? This is binary search. Right? It's just that it's not done in an array. It's now done on a binary search tree, which means that you're not restricted to simply just random access. You don't have to have random access anymore, right? So it's the best of both worlds. It's kind of like a linked list, but it's a tree, and it's kind of and you're able to leverage the power of divide and conquer using binary search. Right? It's not binary search, but it's a binary search tree instead. Right? Okay, next time we'll review this by writing the actual pseudocode. We'll take this outline and translate it to pseudocode. Okay? Make sure that you're picking up your design documents because this is your last chance to get any feedback on it. Homework 6, your JDBC phase is due this Friday. Keep in mind that next week is your last phase is due. That's where you actually have to write a sorted list ADT and incorporate it into your project. And in case you missed it on Piazza, remember we do have an 8th assignment. That's all written. There's no coding there whatsoever. You'll actually write it. Handwritten is fine. LaTeX is great if you know LaTeX. Do not try to use Word. There are too many pictures. There's too much math. You'll be fighting Word the entire time. So handwritten is perfectly fine. If you know LaTeX or want to learn LaTeX, great, go ahead and go with that. But that's due on the Thursday of Dead Week. Keep in mind also that we have a bonus assignment opportunity, homework 9. You have 2 options. One option is to turn in any previous phase for up to 50% of your points back on that phase. Or you can go for up to 100 points by doing a programming challenge that was inspired by a recent Google visit. It's on binary search trees, by the way. Right? So that does involve programming, and it's worth up to 100 points. Go ahead and check that out. It's all available now on Canvas. All right?